Let's continue robot manipulator. This is the dynamics for robot manipulator. Q is the state, and the torque can control the Q double dots as well as Q dots and Q. Usually, the tracking control desired trajectory will be provided. Here, desired trajectory is XD. The desired trajectory to be 0. That means it's a regulation problem. We want X goes to 0. But what we control is not X, but Q, okay? So that becomes a backstepping control problems. And here's are the property we need to use. There are two subsystems in the overall system. So in the first system, what we have is we use the Jacobian relation to convert between joint space and text space. So the virtual control for sure is QD, okay? That is the desired trajectory for Q dots. QD dot is a desired trajectory for Q dot. And that can be designed by simply as a feedback control. And then we get to the system 2. And the control input is tau, which is the physical control input. In tau, you will expect to see nonlinear terms, cross-term feedback terms, to make up the controllers. And the objective is to control Q dot to reach QD dot so that it can ensure system 1 will achieve its objective, which is S goes to 0. So the control problem is control design tau to achieve Q dot, to track QD dot. So the control design for the second system is this. This is the open loop dynamics. Here eta is the tracking error between the two, okay, between Q dot and QD dot. MQ double dot provide the control access for the control input tau. Based on the stability analysis, we design these controllers, okay, these controllers, which consists of cross terms. This is feedback term, this is cross term and feed-forward term or nonlinear terms. And that can be, by substitute this into the open loop dynamics, we got the closed loop dynamics, okay, which is this. Then we can do the stability analysis here, okay? To ensure X will converge to 0. X is in text space. Okay. So virtual control, which is Q, right? Q, and you need to design the desired virtual a QD dot for Q to track. So this can be rewrite as X dot equal to J Q dot. And what's next is we subtract and add QD dot plus J QD dot. Okay. We say eta, define eta as the difference, which is Q dot minus QD dot. Okay. So this become the state of the next system. Okay, because in the next system the objective is for eta to be 0. Right? And in the first system is for X goes to 0. So originally we had two systems. One is this, the second one is this. Second one is this. The robot manipulator VQ plus F. Okay. But the objective adjective is what? Is for this signal to be 0, right? Okay. Because for this signal to be 0, Q can track QD. QD is the desire is the virtual control input. Desired virtual control input. Okay. Okay. So let's go back to here. Okay. This can be rewrite as plus JQD dot. Okay. So this we just leave this term, let it be, okay? And we deal with this term because this is the virtual control input. Okay. So how will you design this control? Well, you can do simply just feedback control. Okay. So we design virtual control QD to be, by observing this equation, you can say I want to design QD dot to be a feedback term, right? This term could be eventually become a cross term, so just let it be, and you design this term for this system to be stable. So simply just use a feedback term in virtual control, and for this equation to be let. And remember, you keep this term because that will be a cross term. So given that, I know that the virtual control has to be designed as J inverse X dots. X, no. Minus feedback minus J inverse X. Okay. Okay? So when you substitute this into here, you will get a minus Kx, which is this. Okay? So let's say as long as eta goes to 0, the further system will be stable. Right? S will converge to 0, which is the adjective. Okay, so eta, as long as eta goes to 0. So for s that goes to 0, you just let this adjective to be the task for the second system. Okay, so the adjective for second system is s eta goes to 0, and then given this objective, you can now find the open loop arrow system. And because this is a tracking error, so now your open loop arrow system has to be defined based on this. So ME eta dot, and eta dot will be M. What? Eta is the mismatch between Q and QD double dot, right? And here is the access for control. So MQ double dot is, now you can use this equation, which is the tau minus that tau minus Vm Q dot minus F minus G. Okay, minus M Q D double dot. But different from the previous analysis, the QD double dot is a defined function again, right? It's a defined function, but QD has coupling with the first equation because QD already has to be defined as this. Okay, so it cannot be any user-defined function. It has to be this because of this adjective. Okay, so for QD double dot, you need to take one more time derivative on this. Okay, that's why I put time derivative here. Okay. Okay. So now control is here. How will you design tau to ensure A tau goes to 0? Just look at this structure. So here, obviously, QDFG. So this FGF and this term is exactly as same as these three terms, right? Okay, so these three terms is used to cancel out these three terms, right? So using that tau, your M A dot dot becomes VM Q D dot minus Q dot GFM goes away. JX minus K eta. Okay. Okay, it becomes this. Right? This. Okay, the same, right? Cross loop aerodynamics. Now let's do the analysis. We design this stable function, okay? And we take the time derivative. Remember that M is a function of Q, so when you take the time derivative, you need to use chain rules, and that N dot pops out, okay? But N dot, we can use skew symmetric property to combine this term and these terms, so that the summation of the two terms will be 0. Skew symmetric property. Skew. So this term, is eta, so we cannot put Q. This eta, okay? Because it's eta. So here, your Q had to be eta times Vn times eta. Eta square and Vm, okay? Eta square Vm, okay? So that will be 0. And then you have And this QD will be cancelled out with this QD dot, right? So only these two terms will be left, which goes to here. Okay, which go here. Then you cancel out the cross terms. This is cross term. This is cross term. This is cross term. Cross term. Okay? Then you got a ND. So that shows both X and A tower goes to 0. So S goes to 0 is our adjective. Okay? So QED. Any question here? 没问题。有没有写错？有 typo 吗 ？Okay. Yeah. So if that's fine, let's go to skew symmetric. Hey. Property 呀、你回去可以试试看。有关，没有 VM 是那个啊，那个 Coriolis。这里。VM is the Coriolis constant. Okay. So if you have property can be used, just use property. You don't need to waste some control effort to cancel out some term that cannot be canceled, right? You save energy. Use property, save energy. You don't need to use control. So property first. And that's the property for general robot manipulator systems. Okay. Any other questions?好，没有问题的话 we have few more backstepping control design case, so don't worry. Here are a few more. So we will use backstepping on some mechatronic systems like motor control. Okay, and we will first introduce the systems that based on the dynamics, and why, and by explain why it can be used. It can be controlled with a backstepping controller, and so that we will compare for you to be a good reference. We will compare without using a backstepping and using a backstepping, and you will see the difference, okay, and the benefit of using backstepping. So first, mechatronic systems, 机电系统, okay. The first system is mechanical system, that is considered as some link, some robot arm linked by joint, and the joint can have a state which called is Q. Okay, and here's the dynamics. And obviously here's the single joint. Over like this, okay, M. You have torque. The center of gravity is here. I just give you that first equation and say let's control torque, right? But the second equation is motivated by the detail control loop or the inner control loop, because we cannot say, oh, give me this torque and you can achieve that torque. In other words, the torque is a function of current, right? Ideally, torque is proportional to current in the circuit or the motor, right? So there's another electrical system to formulate how you can mapping from given a voltage, how you can generate the current. But it's not simply a proportional relation. It's a ODE, it's a first order ODE, okay? In other words, the voltage you provide will equal to the inductor times the time derivative of the current, and Ri plus the angular velocity of the motor. So it's kind of a tricky equation because it not only depends on I dot but also on mechanical system Q dot. Okay. So we can usually consider this as outer loop. Okay, you can apply PID in here, and you have in fact you have another inner loop that is being used to control current. Okay. So the question becomes, if you want to control the angle Q to be maybe to track some desired trajectories, you no longer control torque, but you control the voltage input into the motor. Okay. So the assumption here is we have exact model knowledge. We know M, we know G, we know L, we know the inductor L, the capital L, and we know R and K, all the coefficients, okay? And Q and Q dot are measurable, just for simplicity. And the objective is to design the voltage in the inner loop such that probably you'll be using robust control, whatever control you like. And we want to achieve that Q will track QD as t go to infinity. Okay, we control this V and hope that Q can track the desired trajectory QD. Okay. So if we don't use backstepping, so here, so we can consider mechanical as a first system and electrical system as a second system. So the physical control is V, is the voltage, right? Virtual control will be tau D, okay? So without backstepping, what we can do is we just design, for tracking control, we define the filter tracking area R, okay? And we design the controller here, okay? We design this control, sorry, MQ double dot plus voltage. So using this relation, we can say Okay, so we combine the two equations. Okay, and because tau is proportional to the current. Okay, here's coefficient. The current is proportional to the torque. So we use this relation and substitute the current by using this equation. Okay, we keep I in the left hand side and move the 2 on the right, and then divide it by R. Okay, so this is current. This is current. You control the V here. I was asked how we can implement this backstepping controller. Okay, so see that in this block diagram we don't see eta, right? Where can you find eta? No, eta was not defined in the block diagram, right? It's a virtual signal. Okay, and the potential location of eta can be defined somewhere here. Okay, eta is what? Eta is the signal. It's the error signal between QD dot and Q dot, right? And in the block diagram, Q dot is here, but QD dot is not. It doesn't exist. QD dot is a virtual control input. It's a user-defined signal, right? It's a user-defined signal, and it was defined to be this. It's a function of X. Okay, so when you implement controller, you don't need to implement this. Okay, because it's virtual control. What you need to implement is tau. Okay, and tau, given the tau, it will give you some Q or Q dot, and Q dot will be used to connect with the first system, Q dot here. And that's why you only see Q dot, which is the bridge between system 1 and system 2. Okay, eta, but you still need eta, because in the physical control tau, you might see eta. For example, this is the control you need to implement, and you see eta here. Okay, and eta is a virtual control. Okay, it doesn't appears physically, but it helps you. You can consider eta as a signal. They will have to be implemented in the control. Okay, and the signal is defined as the mismatch between Q dot and QD dot. Q can be measurable. QD dot is defined as this, which is a function of X. Okay. Okay, so that's the way how you implement just the physical controllers, and which might contains the eta signal. Okay, and virtual control is only used to help you do the analysis. So here we say we are, if we don't use backstepping, what you will do next is we design this V. We design this physical control V, and you will put some terms to cancel out these two terms, right? So these two terms are used to cancel out the two terms here, and you might also put cross terms, cross feedback terms. Okay, this is the way you design controllers, and that doesn't require the backstepping approach, because you already combine the two systems together, right? You did not. For backstepping, we divide it into two systems and design two controllers. One is called virtual, one is called physical. But if you don't use backstepping, you just combine the two systems together, right? And this is the way we combine it, right? And the control input is V. There's no virtual control term anymore because you already combined the two. And the way you design V is, so the price you had to pay is this term, I dot term, right? Usually you can measure current, but for its time derivative, it's not guaranteed. Okay, so you have difficulty implement this I dot. Okay, and that's why we want to use backstepping for this kind of problems. Okay, so now let's try backstepping approach. So for backstepping, we have virtual control and physical control. Okay, we have virtual control, physical control. Let's find the virtual control. And because we are doing tracking control, okay, so I will use the filter tracking error defined as E dot plus alpha E. So then for MR dot, I have M E double dot plus alpha E dot. Okay. Then you can substitute this open loop controllers. Let's MQD. Let's define E as Q QD minus Q. Okay. MQ okay. Okay. And then we again subtract tau D and plus tau D, which is the virtual control. Then we got minus tau D, okay, and eta is defined as the current tracking error, the desired current and the current, okay. And W have been, it combines two terms, this term, and, sorry, this is W. This is W, okay? So virtual control can be designed as ID equal to K tau plus WKR. Okay. So let W is used to cancel out this W. And Kr is the feedback term. Okay? And this could be the cross term. And this is could be further decomposed. But anyway, just keep it as it is. So by using the substitute virtual control, the closed loop error system 1 becomes MR dot equal to K tau eta plus alpha m R minus alpha E, which was E dot, okay, minus KR. This is the closed loop error system. And we decompose E dot to be R minus alpha E using this relation.这样没问题。有问题吗？ So next, system 2. System 2, the objective is for eta to be 0. Okay, for eta to be 0, and we have to define open loop error system. I will just write OLES. OLES. Closed loop error system, open loop error system. L eta equal to L ID dot minus Li dot. Okay. And I dot is Li dot is this, right? This equation. You move these two terms to the right. You got V minus Ri okay. And remember, this is the physical control. Physical controller. So we design controller as okay. I will erase this. Which is physical control as allow id dot plus ri k tau. Okay. Okay. Then closed arrow system. I substitute this controller into that open loop arrow system. You got a closed arrow system. That is lambda dot equal to minus k eta minus r transpose k tau. Okay. K tau. K tau. Okay. Arrow system 2. Arrow system 1. Now you can do the analysis. Okay. So when you do the analysis, you just keep CLES 2 and 1. So take the time derivative of V. This is capital V, the above function. Okay. It's R transpose. MR dot. MR dot is this. Okay. K tau eta plus alpha M R minus alpha E minus KR. Okay. Plus eta. Although eta dot is that. Okay, and plus the third term. Third term is this, which is E transpose alpha square M. E dot, and I use R minus alpha E. Now you can cancel out the terms. For example, this is cross term. Cross term is this. Okay, this is the first cross term, and another cross term is this. Cross term. Second cross term. So eventually you will get R transpose K alpha M R minus K eta square minus alpha cubic M E transpose E. Okay, and this is ND provided that K is greater than alpha M. Okay. That is globally exponentially stable. Okay. 자, 没问题。Any questions? And for engineering solution, someone might use PID. And for example, if you use PI, engineering solution, you will design virtual control as just KP. Okay, this is P control, KP, which is a control gain times the current error. You implement this as a control, which is the voltage input. Okay, compared to backstepping, that consists of a lot of terms. In fact, this KP term is same as this term, right? And this term is considered as a feedback term for the feature control. And all these terms are, this is cross term, and this is nonlinear terms, or you can consider feed-forward terms. So basically you can obtain a better performance using these backsteppings. So if you use engineering solutions, what happens is it's considered as a high gain control, and eventually you won't get exponentially stable or asymptotically stable. You will get UUB. Okay, that's the difference. Okay, it's a trade-off. It's easier to implement the engineering solution, but the control performance is not good. Okay, and you will say, if I choose a larger KP, a larger control gain, use a high gain, but it's still not a syntactic tracking. Okay, and it requires a lot of effort because you choose a high gain. Require a lot of efforts to stabilize system. Okay, is this system controllable? Do you think this system can be stabilized by a backstepping controller? What's the virtual control? X1 or X2? 不然再给你们个答案。都不是。If you consider X1 as a virtual control, X1 was not in the second system. There's no relation between X1 and X2, right? 对吧? Can you use X2 doesn't change the dynamics of X1, right? So they don't have any relation. X3 doesn't change the dynamics of X2, right? And go back, look at what we have here. The virtual control is tau, right? And what can you control? Can this second system change the value of tau? Yes, right? Because tau is a function of current, and we have current in the second dynamics, right? In here, in the first system only X1, right? But X1 doesn't show up in the second system. There's no relation. Cannot use this backstepping. Okay. 本来应该叫一个人上来写，然后看他怎么写，蛮好奇他会怎么写。What's the virtual control first system? X1 or X2, or none of those. Before we just discussed second order. Now it's third order. It's higher orders. Right, you have 3 equations. How will you design this backstepping control? 假设你 eta 等于0 x2d 等于那个，那你这样 x1 大会变什么？假设这一项等于0了嘛，然后你那 virtual control 里面下到这一项嘛，所以你会变只有0而已嘛，你没有 feedback term 嘛，所以你还缺什么？要有个 feedback term 嘛，这个就是从你 virtual control 来，干嘛？所以就加上去就好了。对，这样就完成了。So system 1, that's the virtual control. So for system 2. 这是 objective， 先不要看。所以 X3D 要怎么 design 才能得到这个样子 ？Eta 2对。So plus eta 2等于什么？这个减这个。 这样对不对？那你要怎么 design 才会让它变成剩下一个 feedback term？cross term 就先不管。假设这个0嘛，这个就不管嘛。你要怎么 design 这个 virtual control 才会得到这种 first order stabilized system？ 还有吗？缺这项对不对？ eta 就 eta 就好了，嘿，就这样。So this is second virtual control. Okay. So eta in the second system, the objective is for eta goes to 0. So we want to analyze the eta dynamics. So we take the time derivative you got x2d dots minus x2 dots, right? According to this definition. And x2d dot is desired trajectory, is a function of desired trajectory, and x2 dots is equal to x3 based on the open loop dynamics, right? And you can create the virtual control by add and subtract x3d, okay? And now this becomes the tracking error of the second system, okay? So this equal to this, and x3d is the virtual control, and that can be designed as two terms. This term is used to cancel out this. This term is for b back. And this term, just let it be because it's cross term. Okay. And x2d dot is the time derivative of desired trajectory, which means you need to take time derivative on the first virtual control input. And this is the time derivative of first virtual control input. Okay. So it's a bit more complicated. And then we can get to the third system to design the physical control input. The third order system will be more complicated when you implement a controller because it requires several time derivatives on the virtual control input.